Hello, good morning, good evening, good afternoon, good day, whenever you're watching this. Welcome to an intro to organic chemistry for ASAQA. Ignore the thing in the bottom right corner. Thank you. And in organic chemistry, now what is organic chemistry? Organic chemistry is chemistry with the molecules that have the carbon in them. And they're pretty much covalent and they have carbon as like the base structure. So let's get started with the organic chemistry that you learned at GCSE. We have the alkanes and the alkenes. Is it coming back already? So, the alkanes. Now the alkanes come in a series, and so do the alkenes. The alkane series starts with CH4, C2H6, C3H8, and the alkene series start not with one C, C2H4, C3H6. Now these series are called homologous series. Homo for the same, as in same sex homo, but this time it means same group, the alkanes or the alkenes. And with these, because they're the same group, and because, as if you may notice, they differ by CH2 each time. See the CH2 difference there, CH2 difference there, same with here. You can write a general formula for them. For the alkanes, it is C of N. For every N number of carbons, there are 2N plus 2 number of hydrogens. For the alkenes, it's CN H2N, slightly easier. So, back in GCSE, you had to name these up to, I believe, 5, and you had to remember the prefixes and the suffixes of how to name alkanes and alkenes, and a couple others we'll get onto later. Now, the alkanes, you slap an ane on the end, right? Pretty simple. Alkenes, you slap an ene on the end. Pretty simple. But what about the pronouns? You gotta remember those. They go meth, eth, or eth, same with meth, can be meth, pro, bute, and then pent. And afterwards, it's shapes all the way down. Like, you can have a dodecane, like a dodecahedron. Dodecahedron? No, a dodecagon. And then you can slap a thing like methane, but you can't have methene, because alkenes have the double bond, and one carbon means no double bond. Ethane, ethene, propane, propene, butane, butene, pentane, pentene. Simple, right? Let's take an alkane, like butane. C4H, 4 times 2 plus 2, 10. You can represent this in different ways. What I've done here is called the molecular formula. And that just shows how many, how many carbons, how many hydrogens, how many atoms are there in the molecule. You can also represent this as something called an empirical formula, which is C2H5. This is the empirical formula. Now you can think of this as a ratio formula, because this is the simplest ratio of proportions of atoms. So there are, for every 2 carbons, there are 5 hydrogens. See here, for every 2 carbons there are 5 hydrogens, and there's 2 lots of that. So you can represent butane as C2H5 in empirical form. Now you also have the form that draws it all out, so you can see it all nicely displayed in front of you, and that's, funnily enough, called the displayed formula. And that, if we draw it out, is C. You got a C, you got 4 C's. Right? That's the backbone of your molecule. And then you got the H's coming off it, because remember, carbons must have 4 bonds. 1, 2, 3, 4 bonds and everything. There's your 4 carbons, and there's your 10 hydrogens. And from this, you can get what's called a structural formula. Now, displayed formulas, they're very unwieldy, they're very big, and they take quite a lot of time to draw. Like, you have to draw so many lines for the carbons, put the hydrogens on. So people use structural formula to represent these instead. Also makes exam questions slightly more compact. And the structural formula, essentially what it does is it looks at every carbon and what's attached to that carbon and writes that down in a row. So let's take this one. This is CH3, because there's 3 hydrogens coming off the carbon. Don't include the other carbon, because the other carbon is going to come next. This one is CH2, CH2, CH3, and that is the structural formula of butane. And finally, you get something called the skeletal formula, or as some people like to say, the skeletal formula, and that is where you represent things in terms of lines. And it's a type of formula that you see on those chemistry videos where they make crazy things and you say, wow, that looks really complicated, I have no idea what it's on about.
This reaction is formally known as the Baeyer-Drusen indigo synthesis.
So it takes into account the 3D shape of the actual bonds to the carbon. This R is going to be the rest of the molecule, and it draws it out, sort of casts it onto a flat piece of paper. And what it does is carbons are the vertices. So carbon equals a vertex, and you do not draw any hydrogens. Hydrogens are implied. The lines are the bonds. Hydrogens implied, though only if they attach to a carbon. So for butane, it will be 1 vertex, 2 vertex, 3 vertex, 4 vertex, and you draw it in this squiggle like this. You see this squiggle, because this is 109.5 degrees, this squiggle has to be roughly that. But if you don't want to get it to exactly 109.5 degrees, the easiest thing to do is think about hexagons. Just draw it in like a hexagonal form. It's good enough, right? For a different molecule like butene, let's say has a double bond on the end here, that can be drawn like butane, but with a double bond here. You see how there's 2 lines for 2 bonds? This vertex is still a carbon, this one's a carbon, this one's a carbon, this one's a carbon. Any of the remaining unfilled bonds will be filled with hydrogens. Okay, so back to the homologous series, like there's alkene, alkane, and there's quite a few other ones that you need to know. The only thing that's different about them is their functional group. The functional group is like double bond here, and then nothing special on the alkane. It's what makes them react how they are. And I'll show you that right here. There's quite a lot of them. There's also can be quite a lot more. But first of all, obviously we start with the alkane. Right? Just normal old butane. And then you can have the alkyl branches. Branches are a part of a thing called isomerism, which we'll get onto later, in the next video. Don't worry, that is coming out soon. And then you get your alkenes, and these are the, well, these two really are the 2 I was talking about earlier. Alkenes have the C, double bond C, as the functional group. Notice I've done it in skeletal formula, and skeletal formula is nice and clean. Then you have the haloalkanes, where there's a halogen coming off instead of one of the hydrogens. It's like chloroethane right here, but you can also have this be bromoethane, iodoethane, or fluoroethane. Things like these can be really bad for the ozone layer, like chlorofluorocarbons. If you've heard of them, they cause the big hole over the Antarctic and Australia. And those are actually mentioned later in the ASAQA chemistry course. And then you've got your alcohols, with the OH hydroxide, that is OH, functional group right here. And you've also heard of ethanol. Ethanol is the alcohol that gets you drunk. And then you've got your aldehydes. Aldehydes cause cancer generally, so they're not as good for getting you drunk. And they have a double bond O on the end. Note that specifically on the end like this, with that being the rest of the chain. The CHO, that's how it's written in structural form. Whereas this is written CHOH. See? HO, ho, and ho. That's how they not get them mixed up. And then you have your ketones, where it's just like the aldehyde with the double bond O and that alone, but it's in the middle of the molecule, like propanone instead of propanol, where you have C, you have 2 R's, and then you have the double bond O. Okay, and then you get your carboxylic acid. Now, you've done this in GCSE as well, the carboxylic acid, like ethanoic acid. Now, ethanoic acid is also called acetic acid in old-fashioned nomenclature. What a mouthful. Acetic acid is what's in vinegar and what makes vinegar sour. It has the C, double bond the O, and then an OH group. And then you got your ester, where you smash a carboxylic acid and an alcohol together and it'll produce an ester. And the ester is the alcoholyl carboxylic acid OH. So this one is the methyl, because there's one carbon here, ethanoate, because there's the two carbons here. And then you get some new ones like the amine, which has the NH2 on the end, C, N, H, H. And then obviously there's 3 more bonds coming off the carbon. Then you have the nitrile group. The nitrile group is like, it's cyanide. Essentially you can get it by reacting a form of cyanide with a haloalkane in something called nucleophilic substitution that we'll get onto later. Very much later. And finally, you've got your cycloalkanes, which begin with cyclo and have the same name as alkanes. Although do note that whilst alkanes have the general form CnH2n, cycloalkanes, because they all connect into a nice little loop, have the form, oops, that's a +2, have the form CnH2n. No, +2, that is wrong. And those are your main homologous series that you probably should know. Okay, so why don't we go on to drawing some of these molecules from the names? So, let's start naming drawn molecules, all in displayed form. So we start with John. Now John here, first of all, look for the functional group. What's the functional group of John? John's functional group is a carboxylic acid. So John is something oic acid. Okay, and how many carbons does John have? John has 2 carbons, which means it's an ethanoic acid, and that's its IUPAC name, which is what we've been using all along. The IUPAC is used to avoid confusion in the namings of molecules. Now, after John, we got some real bangers over here, so let's go on to Henry. Now Henry, what is Henry? Well, if I look for anything odd, it has 2 chlorines, which means it's a haloalkane, or a halogenoalkane, an alkane that has halogens on it. So it has 2 chlorines, and it's a pentane. So first of all, it is just a pentane, but it's got 2 chlorines, which means it's a chloropentane, but it's got 2 chlorines, which is a dichloropentane. Now, we need to also look for the positions of the chlorines. And since the chlorines are the functional group in this molecule, we count from it so that they have the lowest possible number. For any molecule, always count from the lowest possible number. So, instead of counting left to right, we count right to left as 1, 2, 3, 4, 5 for the carbons, because this is closer to the functional group end of the chain. Which means this chlorine is on 1 and this chlorine is on 2. So that's 1, 2 dash dichloropentane. Numbers are separated by commas, words and numbers are separated by dash. Okay, and the di obviously means 2. You can also have tri, tetra, and so on, but usually that wouldn't happen. And now we move on to Sir Robert Kent Esq. No relation to any real Sir Robert Kent Esquires, of course. Now, this is an absolute monster of a molecule. It's disgusting. But it does have an OH group, so it is an alcohol. We know that, but now it has chains. How do we deal with branches and chains and all of that stuff? Well, step 1, after finding the functional group, of course, find the longest straight row chain, which, in this case, let's highlight it in red. In this case, would be this one. The longest straight row chain from start to finish. That'll be 5. Now, You know, it could be this one, but if it was that one, then you'd have a side group coming off here. We don't want that. So, it's this one. And so, we know that it is a pent something. And now we start the numbering thing, as we did with Henry. From the functional group. Since this is closest to the functional group, it means we start from this side of the parent chain, which will be 1. This will be 2. This will be 3. This will be 4. And this will be 5. And now we look at the positioning. Now remember back to the homologous series, how we have alkyl branches, right? Well, these are those very same alkyl branches. Let's highlight them in bluish. So we got this one. That's an alkyl branch. We got this one. That's also an alkyl branch. We got this one. That's an alkyl branch. Now, we need to know the number of carbons on the alkyl branches. Here there's 1, so it's a methyl. Here there's 2, so it's an ethyl. And here there's 1 again, so it's a methyl. So from that, we know that there are 2 methyls, so remember, dimethyl, and 1 ethyl, which is just ethyl, simply enough. But now we need the positions, because you see here how we have 1,2 dichloropentane. We need the positions for the methyls and the ethyls like we did for the chlorines. The methyl here is on carbon 2, so there's a 2. And the methyl here is on carbon 4, so there's a 4. 2,4-dimethyl. The ethyl is on carbon 3, so there's a 3-ethyl. So now we have pentanol, and then we have 2,4-dimethyl and 3-ethyl in some order. The order here does matter, and the order here is determined alphabetically by this and this. So this is an M, this is an E. In alphabetical placing, these do not count. You don't count the di, the tri, the tetra, the whatever. Okay? That's just a quirk with it. But so, we have ethyl first, then methyl second. So, it will be 3-ethyl. And then, you have dash, because it's a number in the thing. 2, 4, dash, dimethyl pentanol. Which is what Henry is. Henry is 3-ethyl 2,4-dimethyl pentanol. And that's one of the harder ones you'd really feasibly get. It is disgusting, admittedly. Okay, so we've done the overall, the homologous series, or the representation, and we've done naming them in IUPAC names. How about drawing them from IUPAC names? Because you might need to do that in an examination situation that you got yourself in by doing AQA or by doing chemistry A-level. So, we have 3 here. We have methyl propane, 2,3-dimethyl pent 1-ene, and cyclohexane. Now, I'm going to draw them for you in displayed and in skeletal form. So let's start with the methyl propane. So we know that there's 3 carbons on the backbone, and we know there's a methyl there. Note, however, that it doesn't have a number on the methyl, and that's because it doesn't need a number on the methyl. The methyl comes here. Because, right, if it instead came out here, then it would just be butane, because that's the longest chain from start to finish is 4 carbons. Same with on the other side, so it must be in the middle. And then obviously you fill in your hydrogens, because it's an alkane and there's no other special functional groups here. Okay, so that's methyl propane done. Let's give it a name, how about that? Let's call it Barry. So Barry is methyl propane, and now let's draw it in skeletal form. We still have the propane as the backbone, so that's 1, 2, 3. See, remember the hexagon shapes? Gotta keep it in the hexagon shapes, and then it'll look fine. And then there's a methyl group coming off the middle, so there's another vertex here, and it goes like that. There's your methyl propane. Propane. Okay, so let's move on to the next one. 2,3-dimethyl pent 1-ene. Ouch. Ouch. So this one, it's got the pent, so that means there's 5. Okay. And it's an alkene. But the alkene is on position 1. Note, so if we count just left to right, 1 double bond. The double bond comes after the earliest carbon possible, and that's the 1-ene. So now that's pent 1-ene. But now you have 2, 3 dimethyl. So if we count the carbons, with 2, there's a methyl group, and 3, there's a methyl group. And then fill in the hydrogens like usual. And I'm getting worse and worse at this, but that's good enough, you get the idea. Now, how about in skeletal formula? Skeletal formula, we have the pent with a pent 1-ene. So let's start with the pentane, which is 2, 3, 4, 5, like that. But it's not an ane, it's an ene, so we need a double bond. The double bond, so this is carbon 1, that means the double bond goes here like this. And now we need the 2, 3 dimethyls. So this is carbon 2, there's a methyl group. This is carbon 3, there's a methyl group, and you're done. That's 2, 3 dimethyl pent 1-ene. And I forgot to give it a name, Harold. It's obviously got to be Harold. And finally, we have cyclohexane, which I've not given myself enough space for. So, cyclohexane. It's a hexane, so it's a C6, but it goes round and connects back in a loop. So if we draw it like that, we have to draw 6 C's, CCC, CCC, but connect them in a hexagon, in a loop. And then, obviously, you add your hydrogens. Now, I personally prefer to draw these in skeletal form, just because you don't have to deal with drawing this hydrogen thing over and over again. And in skeletal form, you only have the carbons, the hydrogens are implied, you have 1, 2, 3, 1, 2, 3, 4, 5, 6, and connect it back up. And it's a hexagon. And you're done. That's cyclohexane. Now, cyclohexane is a very particular molecule. It's very special. Let's call it Karen. And you know, that's it. That's the first naming and drawing in Intro to Organic Chem. Next video, Isers. Have a good